Hello everyone, this is Kuraizam Jyotsna from the Department of Physics, Manipur University. I am very delighted to present my work on the 12th Biennial National Conference of PANI 2021. Today I am going to talk about the effect of iron substitution on the properties of sodium bismuth titanate. Let me give a brief introduction about the material that is sodium bismuth titanate. In the search for non-toxic replacement for the currently used lead-based titanates in industries, sodium bismuth titanate has emerged as an interesting candidate because of its strong ferroelectric property with large remnant polarization, a moderate piezoelectric constant, and a high Curie temperature. Many researchers are currently working to improve these properties by adopting substitution method and by making composites with other materials. In the present work, pure and iron-doped sodium bismuth titanate having this formula is prepared by the sol-gel autocombustion method. The effects of substitution on the structural, optical, and electrical properties of the samples are studied systematically. This is a synthesis process that is a sol-gel autocombustion method. The precursors we used were sodium acetate, bismuth nitrate, titanium isopropoxide, and iron nitrate. These precursors were dissolved in deionized water and stirred continuously for 2 hours at 80 degrees Celsius to get a homogeneous solution. Ethylene glycol was then added in the required proportion and gel formation takes place. The temperature is raised to 150 degrees Celsius, after which autocombustion takes place and an ash powder is formed. The ash powder is grounded and calcined at 800 degrees Celsius. The calcined powder was mixed with polyvinyl alcohol and pressed into pellets and finally sintered at 1100 degrees Celsius for measurement. This figure 1 shows the excited pattern of pure sodium bismuth titanate NBT and iron-doped sodium bismuth titanate NBFT. All the peaks were indexed with a rhombohedral crystal structure, and in addition we can find an extra peak at the sodium bismuth titanate doped with iron, which may be due to the formation of bismuth titanium oxide. The lattice parameters and cell volume were calculated from the XRD data, and it was found that the cell volume decreased in case of the iron doped sample, which may be due to the substitution of iron, which has a lower radius as compared to the titanium atom. The crystallite size of the samples were also calculated using the Serrer formula, and it was found to be around 40 to 45 nanometer. Figure 2 shows the same image of the sodium bismuth titanate and the doped sample, and we can see that the particles are uniformly distributed with an average particle size of less than 1 micrometer. Next, we have the optical measurement. The absorption spectrum of the samples were measured, and from the spectrum, the optical band gap of the synthesized particles were calculated by using the Taux relation. The optical band gap of NBT was found to be around 2.9 electron volt, and for NBFT it was found to be around 3.1 electron volt. The electrical studies were performed, and the figure 4 shows the dielectric properties as a function of frequency at room temperature. We can see that both samples show the typical frequency dispersion behavior, which can be explained in terms of the space-charge polarization and Cope's two-layer model. Also, we can see that the iron-doped sample has a less dielectric constant as compared to the pure NBT, which may be due to the less polarizability of the Fe3 plus ions substituted in place of the Ti4 plus ions. Figure 5 shows the dielectric constant versus temperature curve at different frequencies for the two samples, and we can see that at all frequencies, as the temperature increases, dielectric constant is increased. This may be due to the thermal activation of charge carriers at higher temperature. The AC conductivity was also calculated from dielectric measurement, and we can see that the AC conductivity increased with temperature, which shows the negative temperature coefficient of resistance, which also shows the semiconducting behavior of the samples. We can also see that the AC conductivity of the iron doped sample is slightly more than that of the pure NBT. This may be due to the fact that oxygen vacancies are created when iron is substituted in place of titanium in order to maintain the charge neutrality. The AC conductivity data were very well fitted with the Johnser's power law and the value of DC conductivity and N, which determines the degree of interaction between the mobile ions and lattices, were calculated. From the table, it can be seen that the DC conductivity increased with increase in temperature. This may be due to the thermal activation of conduction mechanism. Also, we can see that N increases with increase in temperature. This implies that the conduction mechanism in the samples were due to the non-overlapping small polaron tunneling mechanism. So from the above results, we can conclude that pure NBT and iron doped NBT was synthesized by using sol gel autocombustion method. The XRD pattern confirmed the formation of RC3 rhombohedral phase crystal structure. Cell volume of the NBFT decreases as compared to that of pure NBT. Same images showed uniform size distribution of both the synthesized samples. The optical band gap of NBFT increased to 3.1 electron volt from 2.9 electron volt in pure NBT. Dielectric constant is found to decrease in the iron substituted sample, and the Fe substitution increased the AC conductivity of NBT. Thank you for your patience.